I'm very glad to see that so many people have turned up for this workshop in this difficult time. So we're going to be talking about exploring cross-linguistic FrameNet alignment, joint work with Lorenzi. And I'm going to first be talking about the FrameNets around the world, and then about the relation between the FrameNets, and then looking at the frames of all the FrameNets and how we might be able to align them across languages. We have two methods primarily we're going to talk about. One is by synsets, and the other is with distributional vector embeddings. Then we're going to give a short demo of a visualization tool that we've created to study these kinds of alignments. And we'll wind up with some plans, applications, and conclusions. So the good news is that FrameNet is spreading. It's really great to see that there are going to be so many FrameNets around the world in so many languages. We have two new FrameNets that were just introduced last week, Greek FrameNet and Gulf Arabic FrameNet. There are a couple here that are marked with asterisks, meaning that the projects are sort of in several different people working on it in slightly different ways. But in all these places, new FrameNets are being built. So the question arises whether these lexical databases can be aligned to form a sort of unified or at least aligned database, and what would that enable? So how different are they? How similar are they? Well, all of them use semantic frames as a basic structure. Most of them have adopted the Berkeley FrameNet frames to some extent. And all the projects in general are reporting that the Berkeley FrameNet frames are generally applicable to their language to a fair degree. So some have followed Berkeley more closely, such as Spanish, Japanese, and Brazilian Portuguese. Others have diverged more, such as German, French, Swedish, and Chinese, adding a lot new frames or modifying the Berkeley FrameNet frames. And we need to recognize that equivalence is not the only possible relation between frames. Frames in one language can be broader or narrower than frames in another language. And there are certain kinds of differences in point of view or choice of frames that are very regular and extensive. And some of those are well studied, such as the difference between satellite frame languages like English and German, verb frame languages like Spanish and Japanese, and there are other systematic differences. So in looking at this large amount of data, we felt we needed some objective measures of how closely other FrameNets align with Berkeley FrameNet and with each other. And on the one hand, this allows us to study fundamental research questions. To what extent are semantic frames really similar across languages? Are there some frames that are essentially universals? And also think about practical applications of this. If we know that frames are equivalent across languages, it might help us improve machine translation, cross-lingual question answering, information extraction, and so forth. So there are both theoretical and practical implications in being able to align frames across languages. In order to study this better, we have built a visualization tool called VitoXF. I'm not sure the official pronunciation. You'll have to ask Arthur, which allows you to try different kinds of alignments and see what they do in terms of matching frames from language to language. So we've been able to gather, thanks to cooperation from these FrameNets, the data of these languages into this alignment tool, so that it's possible to study the alignments between each pair and Berkeley FrameNet in each of these languages. So we need to think about what that means and how we go about doing it. And it seems, you might think from the beginning, well, they're using many of the same frames, many of them have the same names. Can't we just assume if they have the same name that they're the same frame, they mean the same thing? And the answer is actually probably no. And there are also those that don't match. So in some of the projects, the frame names are not in English, but the data includes a field for the Berkeley FrameNet frame or the Berkeley FrameNet ID, which can be used to align. But even when the names match or the IDs match, the frames may be defined pretty differently. And they may have more or fewer core frame elements than Berkeley FrameNet. So we don't worry so much about the non-core frame elements. But if the core frame elements are different, then they're not the same frame. So what we found to be really useful is to try to align them by the translation of lexical units. So the basic principle is kind of simple but important. So if frames are equivalent across languages, we would expect the translation of all the lexical units in one source language frame to fall into the same target language frame. Of course, this depends on the accuracy of the translations. In a sense, a lexical unit in one frame is one sense of a lemma. That's kind of what it's supposed to mean. So in principle, that should restrict the range of possible translations. So you shouldn't have a wide range of translations. But exactly how to use frames and frame relations in translation is not completely clear. So one approach we've taken is to use the open multilingual WordNet, which has multilingual synsets, each containing words from dozens of languages. So it looks kind of like this. On the left, we have frames in a source FrameNet, and on the right, those are a target FrameNet. And here we're talking about the frames and their lexical units. But because synsets are made up of lemmas, not of lexical units, they don't have definitions, for example, we're going to shift to using lexical lemmas instead of lexical units. And when we do that, we have to recognize that cases like this on the left, where lemma 3 is an ambiguous lemma. It's in two frames, meaning it has two lexical units. So two senses of the same lemma. So when we try to align using synsets, we find some interesting phenomena. So in some cases, we have a relatively simple situation where a lexical unit in the source frame aligns to a lexical unit in a target frame through one synset. The degree of alignment in this case is the number of lemmas that align divided by the number of lemmas in the frames. So in this case, we have two lemmas that align out of four lemmas in both frames together. So it's a 0.5 alignment. So this situation gets more complicated, of course, like here, for example, where lemma 3 is in two frames, and it happens to work out nicely that it's also in two synsets. Lemma 7 is also in this frame. So that sort of implies that they mean the same thing, even though one sense of 3 is in another synset. And then we have one lemma on the target side that matches these two synsets. So we have a total of 3 lemmas matching, and we have a total of 7 lemmas in the two frames. So we divide 3 by 7 to get the degree of alignment. And we worked out a few other measures for this that take into account the fact that sometimes one frame is much larger than the other. So this is one way of aligning along synset lines. We could also think about the frame elements. In theory, they should be the same number and same types of FEs. And some FrameNets have copied Berkeley FrameNet definitions and the FE names and definitions. So you would assume that those are the same. But in others, you have translated names or new FEs have been created. We can try to align those using the crosslingual vectors, which we'll talk about later, to represent the meaning and see if they're the same. FrameNet Brazil and Salsa happen to have FEs in both languages. So we have to handle it both ways and then sort of average the two. So this is another way of looking at alignments. And then we also want to try to do alignment by distributional similarity of LUs, that is word vectors. So one way of using the word vectors is just another way of getting translation equivalence. So we'll use the fast text vectors in many languages, and they're mapped to a shared space for all languages, shared vector space. And these are accessed using the Muse library in Python. So if we look at this diagram, these vectors represent words, lemmas in the second language. And the green dotted line represents a word in the first language. So we define a space within a certain vicinity of the word in the first language, L1, So we only consider lemmas in the second language that are within that limit. And then we look for the closest ones, and we can set a limit K of how many we want to look for and treat all of those as being translation equivalents. And then we proceed as for the synset method. Another method is to take all the vectors from all the LUs, all the lemmas of each frame in each language, and get a centroid by averaging them for each frame, and then seeing the frames from L1, the frames from L2, which centroids are closest to each other, gives us a kind of alignment. So we can just compute the cosine similarity of each pair of centroids. So another way is to begin using BERT vectors. This is a recent type of vector that's very popular now, and I'll let Arthur talk about that.
Hi, everyone. And as Colin mentioned, BERT vectors, they're getting more popular nowadays. And well, one of the, even though multilingual BERT exists, its pre-training doesn't enforce language alignment. That is, even though they're trained with multiple languages, we don't have any guarantee that similar words will be close in that space, multilingual space. So we fine-tune BERT to reinforce this alignment at word level. And from this alignment, we decided to take the average contextual vectors of the annotation targets of each LU in FrameNet. Next, please. So what this fine-tuning does is basically take multiple words that we know are the same, but in different languages. And this figure, for example, they're gonna be each point and the shapes, same shapes represent same words and the colors of the languages. And we want to bring closer the same words in different languages. So the image on the right represents this, while the left is the pre-trained word. Gonna go next, please. So taking this, taking FrameNet annotations, the LU instances for each LU, we take their average, and this is an example of some known pairs that we know that should align. So for example, we have both risky situation, dangerous LU, and risky situation, peligroso, and the same with business company, business empresa, and similarity, different and diferente. And I also took the representation for size colossal and identicality same, because they're not related, but I want to show what happens next. So this is when we use the pre-trained BERT. Obviously, we can see that the LUs that should be closed are not closed. Can you go for the next slide, please? After our fine-tuning procedure, we can see that now we have in that space company closer to empresa and different closer to diferente, and also same. That is something expected with distributional representations. So even though they're the opposite, we have them very close. But you can see that colossal on top right, it's still there, very close to peligroso. So this procedure works for a lot of pairs, but we still have some LUs that we don't fully understand why they're in that space, that we need to do further analysis. Okay. Can you stop sharing now, Colin?
Mm-hmm.
Yes. Now I'm gonna show you a little bit of the tool, how it works. Colin mentioned two different techniques, and I'm gonna show only two. One is using the synsets for translation, and the other one is using the Muse vectors. So this is our interface here. And here I took some frames. I selected the motion frames, both in English and Spanish, but you can see the tool is showing more because a lot of other frames have some alignment score that is greater than 0. So using this option, I can restrict the visualization to only the motion frames, and you can see that there are not a lot showing up. But when I lower the score threshold for the visualization, I can see more. And when I get here, for example, I can expand the matching of cause fluidic motion in English. And you can see that it matches both cause fluidic motion in Spanish and fluidic motion only. And if I click on this edge, we can further analyze in more detail the specific alignment between those two frames. And on the left side, we have the LUs in English. They're color-coded. Yellow are the LUs that we didn't find any translation on the other frame, and green are the matching ones. And if I hover over them, I can see the synsets that this LU is in. I can also hover over the synset, and I can see more details on that, and I can see the right side where it connects to. This allows us to see which synset was used to say that one LU translates to the other. Moving on to Muse vectors, I have another selection here, both, again, English and Spanish, of the activity dash something frames. And moving the threshold again, we can see more. And when I expand the match between activity resume between English and frame, instead of seeing synsets now, the LUs are gonna bring up just words. In the Muse space are the neighborhood. And you can see here, resume, one of the words that it's close in its neighborhood is iniciar, and that's why it matches. I can also tweak here the size of this neighborhood. So I change it to 3 now instead of 5. And the similarity threshold that Colin mentioned, I can move it and changing the way everything is scored. And this also changes this diagram here. That is like the frame visualization. So the tool is all about changing these parameters so we can explore and analyze how each technique differs in the weighted lines. And you, of course, feel free to ask questions at the end. Colin, can I go back to you?
Okay, let me share my screen again. Okay. So thank you very much for the demo. So what can we deduce from this? We can evaluate these methods and various criteria. So if we think about the synset-based methods using WordNet and open multilingual WordNet, the advantage they have is that they are large-scale curated semantic groupings of lemmas. So they have human knowledge built into them. However, the main problem we notice with them is they just have too many senses, and many are very difficult to distinguish. There are dozens of examples. I'll just give you one. Charge 2 and charge 7 in English WordNet. The example sentences for these are, he charged the director with indifference, and the defense attorney charged that the jurors were biased. And the first one is supposedly a synonym of accused. The second is defined as make an accusatory claim. So they really don't seem distinguishable to me, and I think a lot of people would have difficulty with it. And that's the case in many of these synsets. Then think about the vector-based methods. It has some nice features. You can measure distances between lexical units or lemmas with these. There are a variety of them. There's word2vec, glove, and BERT, and there are different ones that get slightly different results, but they have the same basic principle. And you can also try to compose them using mathematical operations to get the meanings of larger units. such as phrases and sentences. There's a lot of active research on that, but doesn't seem to be conclusive yet. However, the downside is that they're really not interpretable by human beings. And when things happen like this enormous, gigantic size being with the other LUs that we were looking at, it doesn't sort of make any sense, and we don't know what to do about it. Also, they're based on word forms and not lemmas or lexemes, so they don't put singular and plural or present and past tense together. And in most of these approaches provide only one vector per word form. We're able to get around that a little bit by using the FrameNet annotated, FrameNet sentences for annotation. Another mixed feature of this is that they encode some subwords, but those are usually not morphemes. So sometimes they are morphemes and that's helpful, and sometimes they're not morphemes and that's kind of useless. So given this, what are we going to do next? Well, we're going to finish our work on English to Chinese because those vectors are not available. And then we're going to prepare this tool and data files for it in all the languages possible and distribute it. The other thing FrameNet would like to do is expand to a wider range of genre, which we've already begun by annotating the TED Talk. This has applications we'd like to test on NLP tasks and on other downstream applications such as question answering and social network extraction, which FrameNet has already been used for. So we find that the experiment in putting the cross-lingual FrameNets together form a good resource for cross-linguistic semantic framing and to research on this. We have measures to judge this. We have a tool for visualizing it. And we hope that you will join us in this research. This work is supported by NSF. And of course, we're very grateful to the FrameNets for providing their data for this purpose. So thank you very much. Please stay well.